So in this video, I'm going to take you through some examples of solving absolute value equations or inequalities. And what I really want you to remember is that absolute value is distance from zero. And depending on where we're at, we can be to the left of zero or to the right of zero. So having that in mind, we have to have two pathways every time when we're solving absolute value problems, assuming that we can do them, because absolute value is distance and it has to be equal to a positive value. So if it's equal to a negative value, we can't do it. So while we're setting up for our pathways, what I want you to remember is, actually I want you to remember three words. I want you to remember less than and, which means everything else would be or. Okay, so when we're setting up our pathways, that's going to be important. So let's go ahead and get started with our first problem. So I can do it because I have distance equals to a positive. So because I can do it, I need to rewrite without absolute value. The first time you rewrite what you see, it's not a less than, so it's going to be or. The second time you rewrite what you see, so the expression in the absolute value never changes, but the answer changes. And after you have the two pathways, you're allowed to move on and solve each equation. You're not allowed to do work where you have absolute value. A positive divided by negative is negative. And a negative divided by negative is positive. These are the answers, and I'm going to go ahead and check them really quickly in the original equation. If I put negative 6 in here, I'm going to have absolute value of negative 3 times negative 6, which is 18. And absolute value of 18 is 18. That is true. If I put 6 in here, absolute value of negative 18 would be 18, and that is true. That is number one. Number two, can I do the problem? I can do the problem because it's equal, absolute value equals to positive. So because I can do it, I'm setting up my two pathways. First pathway is what I see without the absolute value. Stop and think about the word. It's not less than, so it's or. Second pathway, what you see in the expression equals to the opposite value. Solve each equation the way you would solve a simple equation as before. You want x by itself. All right, that's half of the answer. Let's go back to get the other answer. All right. Let's go and check them. If you check the first one, if you put x in 3 in there, you would have 2 times 3 is 6 minus 1. Absolute value of 5 is 5. That is correct. And if you put negative 2 in there, you're going to have negative 4 minus 1, which is negative 5. And absolute value of negative 5 is 5 because the negative 5 value is 5 units away from 0, the number line. So that is correct. Number 3, be careful with problems like number 3 because the absolute value is not by itself. So before you get started, make sure that the absolute value is by itself, which means I don't want the 3. It's a factor, so I'm going to divide both sides by 3. So I have absolute value of x plus 7 equals 4. Now that I have the absolute value by itself, I'm starting the thinking process. Distance equals to positive, so I can do it. My pathways. First, you write what you see without the absolute value. Stop and think about the word. It's not less than, so it's still or. The negative answer. So never change the expression of the absolute value. Never. It always stays the same. That's always the case. Let's solve for x. You're adding two negatives, more negatives. So this is what I got. I'm going to check it really quickly. If I put negative 3 in the original, 7 minus 3 is 4. Absolute value of 4 is 4, and 3 times 4 would be 12. 3 times 4 would be 12, so it works for the first one. If I put negative 11, the original, which was the Greek problem, the green problem, negative 11 plus 7 is negative 4. Absolute value of negative 4 is 4, and I'm still having 3 times 4, which is 12. So it works. Now, when we're working with absolute value equations, usually we're not asked to graph. because think about it, the graph would be dot, 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 dot every time. So it's going to be kind of like not of interest, 2 dots, that's about it. Let's go to the next screen right now, where I'm going to show you how to solve one equation and then 2 inequalities. So if you're looking at number 4, the absolute value is by itself, okay? And because it's not equal to a value, I don't know if this value would be positive. I need to be very careful when I'm done with the problem, because I might have a solution that doesn't work. So I really have to go back and check it. We check for, as we call it, extraneous solutions, something that might not be working. So let me set up the pathways first. Again, we're thinking about the same thing, less than and. It's not a less than. So in the middle, you should have or. So x plus 5 equals to what I see. That's one possibility. Or x plus 5, that never changes, would be equal to the negative of that expression. So here I have to get x's together. I'm getting rid of the smallest. So 5 equals 2x minus 7. Put your numbers together. 12 equals 2x, divide, and x equals 6 from here. Let me go to the other side. Be careful with the other side. You distribute the negative, which means negative 1. And negative times a negative is positive. Put your x's together. This is the smallest x. 4x plus 5 equals 7. Put your numbers together. 4x equals 2. And then if you divide both sides by 4, you would get x equals a half. So you got x equals 6 or x equals a half. I still have to go back and check to make sure it's working for both. So let's go back and check them both. All right, if I put 6 in the original where x is, well, 6 plus 5 is 11, and absolute value of 11 is 11. Let's go and check the other side. 3 times 6 is 18. 18 minus 7 is 11. So 6 is working for sure. That is a good one. If I put a half plus 5 is 5.5, which means 5.5, and absolute value of 5.5 is 5.5. Let's go to the other side. 3 times a half is 3 over 2, right? Which is 1.5. And 1.5 minus 7 is negative 5.5. So this is not working. This is not a true statement, which means I can't accept this. This is an extraneous solution. It's not making the original problem correct. So in this specific case, I'm going to accept only the one answer. So that is with equations. Let's go to inequalities now. Remember the same thing, what I said before, less than and. Let me grab a new marker. Let me make sure my line is thin, and let's get started. All right, I don't have the absolute value by itself. So I'm going to divide by that factor of 5, and it is a positive value. So I don't have to switch the inequality symbol. 15 divided by 5 is 3. Now, I still have pathways. It is a less than, so in the middle I would have to put the and word. And it's kind of the same as far as what the expression in here is. It never changes. The first time you rewrite what you see with the absolute value. Be careful with the second pathway. Expression never changes, but you have to switch and switch, or flip and switch. Both of them, the symbol and the answer, are switched for the second pathway. That is the rule, so don't forget that. And then after that, you're just solving the equality, y by itself. Y is less than 0, and y is greater than negative 6. Now, this is the answer to different things. Because this is an end problem, I'm allowed to put them together only for end problems. Remember, and isn't like y has boundaries. The smallest boundary is negative 6, and the biggest is 0. We like putting it this way because if you're asked to graph, it's easier for you to see how the graph goes. So if I go here and I put some numbers in, negative 8, negative 6, negative 4, negative 2, 0, 2. This is telling you, let me just grab another marker, open, open, and y can be anything between them. So you can have anything from -6 to 0, but you can include the boundaries, you can include them. And that's how you show it. So everything that is shaded is a solution. So here in inequalities, a number line or a graph makes a lot of sense and it's of interest because it includes all the solutions we can have. Let's go to number 6. I'm just going to grab really quickly another marker, and I'm going to make sure it's thin. And I'm ready to get started. The first problem I have is that I don't have the absolute value by itself. So let me get there. 1/2 times the absolute value greater or equal to 4. I still don't have the absolute value by itself, so I have to get rid of the fraction. So I'm going to multiply both sides by the reciprocal, which is 2. So I'm multiplying by a positive, so there's nothing for me to switch. Multiplying by positive both sides. All right, so let me just go ahead and grab another marker. I want it to be thin again and move on with my work. 2 times 1/2 is 1. So I have absolute value of 2w minus 1 greater or equal to 8. All right, so now I'm ready for the pathways because I have the absolute value by itself. It is not a less than, so this would be an or. So rewrite what you see without the absolute value. Or expression never changes, but you have to flip and switch every time with the second pathway, every time. Doesn't matter if it's less than or greater than, it doesn't matter. That's the rule. So now I'm solving to get w by itself. That's my goal. And then I divide by 2, and it looks like I'll have fractions here, and that's fine. It can happen. W is greater or equal to 9/2, which is 4.5, or W is less than or equal to -3.5. Now, this is not an end problem, so I cannot rewrite this. This is what it is. I can still go and show it on the number line. So let me just really quickly here. I'm going to try to make the number line here in the middle, so I don't have to switch the screen so you can see what I'm talking about. So let's say this is -4, and let's say this is 0, and let's say this is 4. So this side tells me go at 4.5, which is right here, closed. Let me just grab quickly another marker. Closed, and go to the right, and then closed on -3.5. Well, if it's -4, this is going to be -2, -3. -3.5 would be right here. Closed, and go to the left. Again, this is of interest because it includes all the solutions. Similar to what we have said before, an end problem shading between the circles, and or problem shading outside of the circles.